I'm Mike Brim from Oak Ridge National Lab. I'm a senior R&D staff in the National Center for Computational Sciences. I'm going to give an update on some of the work we've been doing with DAOS at the Oak Ridge Leadership Computing Facility. So if you attended the virtual DUG back in May, you've seen this slide before, but I'm just going to recap it because it's motivating what we're doing. In leadership class computing, we're increasingly seeing the use of scientific machine learning and artificial intelligence workloads. Unfortunately, they differ quite a bit in their I/O patterns from traditional mod sim. So we're seeing high metadata rates and also high random read IOPS. And of course, as you grow these workloads and scale them up to capability class machines, the demands only increase. And what we've seen with our existing parallel file systems, such as Lustre or GPFS, is they struggle a bit. I mean, they work, but it could be better. And so this is primarily due to the fact that historically they've been designed for large sequential reads and writes, and they don't really understand how to deal with the kind of the non-temporal spatial locality that you get from caching benefits that are built into these parallel file systems. So when we put out the request for proposals for OLCF6 discovery, we actually asked vendors to say, hey, what are you capable of doing with respect to something that's more optimized for AI workloads? And we started an evaluation of different technologies to kind of inform our decision when it came around to doing selections. So a few weeks ago, you guys might have seen the fact that Discovery's basic configuration has been announced. Discovery is an HPE plus AMD GPU and CPU machine. We're targeting availability to users in early 2029. And the interesting bit is we're going to use the HPE Cray supercomputing storage system, K3000, as our DAOS for AI optimized storage. So as I mentioned, even before the RFP was released, we started evaluating different technologies. This is an overview of our test bed that we have in the OLCF advanced computing ecosystem. It's basically an open development environment at Oak Ridge. So we have 8 DAOS servers based on Supermicro boxes with dual Intel processors, 64 processors, and 512 gigs of RAM. These are dual NDR200 network connected, and each server has 10 3.8 terabyte NVMe drives, so we're roughly 300 terabytes total. We're doing 2 engines per, so it's 16 engines and 320 targets across those drives. For compute clients, what we have are some HPE Apollo 2000 Gen 10 boxes. So it's basically four nodes in a I think it's a 4U. But each client has an Intel Xeon Gold with 256 gigs of RAM and an NDR NIC. For evaluating software purposes, our latest installation is 263 of DAOS. Based on some earlier testing, and I mentioned this last May, libpil for DFS is our best current solution for interception for POSIX workloads, and so any results you'll see today that are based on that. We're still just testing with the default POSIX container config, not doing any redundancy. Part of that is motivated by our current thinking about how we might use such a system is it might be a per job resource where you're moving data in from the parallel file system, then using DAOS for random read workloads, and then throwing it away when we're done. And so we may not need redundancy for these data sets that are already stored on other systems. So we don't have any storage class memory in these, so this is the metadata on SSD configs. So the software that we're using to test these things, so one is Elbencho. I introduced this back in May. It's essentially yet another I/O and storage benchmarking thing. It's not MPI based, which actually makes it more interesting. So there's less, kind of synchronous behavior that you would see in ModSim. And so we've configured that. I've not tested Lbencho to scale, so I can't speak to how well it would actually scale up to a very large compute machine. But for our purposes, it works really well and it's highly configurable. The other thing we're using is the DLIO, the Deep Learning and IO benchmark, which is a product of Argonne and some of our friends at Livermore. So I presented some initial versions of these results back in May, but this is based on the results that are more statistically relevant. So the initial results I presented in May were essentially single runs and kind of early behavior. This is, the kind of the average of at least 5 runs behaviors. So in this evaluation, what I'm looking at is what happens when you construct a data set of a bunch of small files. In this case, I'm showing the results for a data set that is composed of 32 kilobyte files, where there's either 256K, 512K, or a million files in each data set, and then running these results across 4, 8, 12 nodes with 48 processes per node. And this is a workload where it simulates AI epochs. So there's 4 training epochs, and the behavior is such that we copy the data set into at DAOS, then we run the first epoch. So that's kind of the hot behavior, and then there's the reread behavior for the other epochs. And so the way that this is reported is what's the behavior of epoch 1 and what's the average behavior of all subsequent epochs. And so in the graph here, you'll see pairs. So basically, if you look at the first, the leftmost graph, there's a blue and an orange. So the blue is the epoch 1, and the orange is the epoch K average. And so you do see that DAOS is able to effectively give you at least some performance advantage for the rereads. And the other thing we see in this graph is as you move farther right in each figure, that's increasing the number of nodes. And so as we scale up, we are, at least for the first reads, seeing some scaling behavior, whereas the average behavior for the subsequent reads is not really gaining anything, but it is roughly maintaining a constant top-level behavior. So the other type of data sets we're considering is essentially a single large file. So you can imagine this is just a data set with a bunch of records of various sizes, but it's read by clients randomly, and the sizes of those records may vary. But in this case, what we're doing is we're reading 32 megabytes as the record size, and simulating data sets from 384 gigs up to 6 terabytes. In this case scenario, we're using 24 processes per node. The results are similar for 48. They don't actually get a lot better by throwing more processes into the mix for this case. And then here you actually see for the shared file case, which makes a lot of sense for DAOS because it's designed to accelerate, parallel ModSim. We actually do see, scaling increases as we go up from 4 to 12 nodes. And, still see some caching benefits. So the last benchmark that I'd like to tell you about is DLIO. So we took existing DLIO as it stands and ran it, but the data sets are too small. So I talked to the developers and they're like, yeah, just scale it up and that's fine. It'll keep the same patterns. And so in the configurations we're using, we ended up with a ResNet that was 2.7 terabytes in total size. So ResNet uses about 20,000 files. Each one of those is 137 megabytes. For CosmoFlow, it's over 2 million files, but they're smaller files. But the total size is 6.8 terabytes. And the IO threads and the samples per batch, those are kind of the default configurations for DLIO. But what we see down here at the bottom is as we increase from 4 to 16 nodes using 24 processes per node, we're getting, for ResNet, it starts out with almost linear scaling and then trails off a little bit as we get to higher counts. CosmoFlow doesn't do quite as well, most likely just because it's processing more and more files. But the the takeaway message is we do see, increases as we go up in the number of nodes. How far out these go, I can't tell you because, we only have 16 client nodes to play around with, but at least from our perspective, it shows better performance. And I'm not showing you the results from other systems that we've tested so far because that's not an apples to apples configuration. We have a different storage system that we've also run these tests on, but it's not on the same hardware, so it's not worth comparing across the two. But the takeaway message is we believe that DAOS will be a suitable resource for doing, scientific ML and AI and accelerating that versus what you can get out of the parallel file system. We are currently working on the paper that has the results for DAOS as well as other storage systems. We will also be releasing our evaluation software, which is basically a meta benchmarking that includes a bunch of IOR, a bunch of other things, all nicely configured so you can run tests across different storage systems. We do have some results with data protection for like IO500, but not for these. Yeah.
How do you see DAOS overall integrated into your overall infrastructure from a storage standpoint? Like you copy data just for the run and you do the run?
So again, the thinking that aligns with these experiments is data that you need to keep long term lives on a durable, redundant storage system, most likely a Lustre or some other shared storage. And then we're just moving the data we need for that particular job into essentially a container that is accessible for that job. It uses it. It may, we'll talk about policy decisions later, but this is just kind of the current thinking. And then we can just throw away the container when we're done. And we
integrated with the resource manager as you schedule the job?
It's possible. We don't have exact plans at this point because we're still kind of discussing what's the best for usability and yeah.
Any other questions? If not, thank you, Mike.
Yep.